Hello everyone, my name is Xiong Sen Chuan, and together with my team, Izayumi, Matthew, Wafiq, and Nurin, we are going to present our project on the DC to DC buck converter. So, what is a buck converter? As shown here, buck converter are essential non-isolated DC to DC switching circuit used for efficient voltage step down in application like motor drive, battery chargers, and regulated power supplies. So, our project specifically focused on the design, simulation, and partial hardware implementation of buck converter with the following specification, which is 28 watt as input voltage, 14 watt as output voltage at 35 watts. The switching frequency we choose are 40 or 20 kHz. Our main objective to achieve a regulated output with minimal ripple, which is under 4%, to validate our theoretical calculation through simulation, and to understand the practical design challenges involved. With that, I will now hand on to my teammate to walk you through the design and simulation phase.
So today I'm gonna present about operation principle. A buck converter operates by rapidly switching a transistor on and off to control the energy stored in an inductor. The duty cycle of the switch determines the average output voltage, which is lower than the input voltage. The inductor and capacitor smooth the current and voltage to provide a stable DC input. So for step-down DC-DC converter, it uses high frequency switching. The inductor store and release energy. Duty cycle will control the output voltage. Output voltage is lower than input voltage. Lastly, the capacitor smooth the output voltage.
So next, I will be explaining about a DC to DC buck converter and its performance based on MATLAB simulation. A buck converter is used to reduce a higher DC input voltage to a lower DC output voltage. In this project, the buck converter is designed to produce an output voltage with less than 4% ripple. So this slide shows the buck converter circuit configuration. The main components used are MOSFET switch, a freewheeling diode, an inductor, a capacitor, and a resistive load. The MOSFET is controlled using a PWM signal generated in MATLAB Simulink, and the inductor and capacitor act as a filter to smooth the output voltage and reduce ripple. So this is the result that we have obtained from the MATLAB Simulink simulation. There are three waveforms, which is the first waveform shows the PWM signal applied to the MOSFET. The second waveform shows the inductor current, which has a triangular shape and does not reach zero. This indicates that the buck converter operates in continuous conduction mode. And the last waveform shows the output voltage of the buck converter. This figure shows that the output voltage increases smoothly and becomes stable. From the simulation, the output ripple is observed to be less than 4%, which meets the design requirements. The low ripple is achieved by selecting suitable values for the inductor and capacitor. So this is the result that we have obtained from the MATLAB Simulink simulation. There are three waveforms, which is the first waveform shows the PWM signal applied to the MOSFET. The second waveform shows the inductor current, which has a triangular shape and does not reach zero. This indicates that the buck converter operates in continuous conduction mode. And the last waveform shows the output voltage of the buck converter. This figure shows that the output voltage increases smoothly and becomes stable. From the simulation, the output ripple is observed to be less than 4%, which meets the design requirements. The low ripple is achieved by selecting suitable values for the inductor and capacitor.
Let's walk through the key calculation for our buck converter design. Our goal is to step down from 14 volts to 8 volts, deliver 35 watts, and keep output ripple under 4%. So we start with the duty cycle. For a buck converter, the output voltage is the input times the duty cycle. Here, duty cycle D is set to 0.5, meaning the switch is on for half the period. Next, we calculate the load resistance using the power equation P equals V squared over R. We rearrange to find R. 14 squared is 196 divided by 35 watts give us 5.6 ohms. This draw 2.5 amps at full load. The switching frequency is 20 kHz, so the period T is 50 microseconds. Inductor current equals load current, so at 14 volts across 5.6 ohms, that's 12.5 amps. Now, the inductor. The minimum inductance for continuous conduction is given by 1 minus D times R over 2F. Plugging in number 0.5 times 5.6 divided by 4 40,000. Let's walk through the key calculation for our buck converter design. Our goal is to step down from 14 volts to 8 volts delivery 35 watts and keep our output ripple under 4%. We start the duty cycle for a buck converter. The output voltage is the input times the duty cycle. Here duty cycle is set to 0.5, meaning the switch is on for half the period. Next, we calculate the load resistance. Using the power equation, P equals V squared over R. We rearrange to find R, which is 14 squared is 196 divided by 35 watts, give us 5.6 ohm. This draw 2.5 amps at full load. The switching frequency is 20 kHz, so the period T is 50 microseconds. Inductor current equals load current, so at 14 volts across 5.6 ohm, that's 25 amps. Now, the inductor, the minimum inductance for continuous conduction is given by 1 minus D times R over 2F. Plugging in numbers, 0.5 times 5.6 divided by 40,000 give 70 microhenries. When then apply a factor of 10 for safety, resulting in 700 microhenries. Finally, the capacitor is sized to limit ripple. Using the ripple equation, ripple ratio equals 1 minus D over 8 times L times C times F squared. Setting ripple to 0.04 and solving for C give us 5.58 microfarads. These values 0.5 duty cycle, 5.6 ohms load, 700 microhenries inductor, and 5.58 microfarads capacitor form the backbone of our design, ensuring stable 14 volts output ripple with minimal ripple.
So for next, I will explain about component selection. For MOSFET, we use IRF520, which is low RDS. It has high-speed switching that's suitable for 40 kHz. Next, diode, we use Schottky type, which has fast recovery and minimize switching losses. For inductor, we use 43.75 microhenry to ensure the CCM operation. For capacitor, we use 100 microfarad. It will reduce ripple and has 50 volt rating for safety. For driver circuit, we use IRF520 gate driver. It will ensure clean switching transition. For lastly, load that we use is 5.6 ohm. It will dissipate 35 watt as per design.
In the simulation slide, you can see that the buck converter performed correctly, producing a stable 14 volt output with ripple within 4%. However, when we moved to the hardware part, the result was different from the simulation. During testing, the hardware experienced a short circuit, which prevented us from obtaining proper output readings. After checking the circuit, we found that the short circuit was caused by one faulty component. This component failed internally and created an unintended connection between the input and ground. Because of that, the hardware could not follow the expected behavior shown in the simulation results. As for the engineering reflection, throughout this project, we improved our understanding of buck converter design, especially how duty cycle, inductor and capacitor values affect the output. The biggest lesson came from the hardware phase, where a faulty component caused a short circuit. This experience showed us that real hardware requires careful testing, proper assembly and patience when troubleshooting. Even though the hardware didn't fully work, the project strengthened our problem-solving skills and teamwork. As for the improvement suggestions, for future improvement, we suggest to test all components before soldering to avoid failures, use current limiting protection during first power up, improve layout and wiring to reduce the chance of short circuits, and also test the circuit in stages instead of powering everything at once, and lastly, to keep spare components ready for replacements. These steps will help to make the next hardware prototype become more reliable.
To bring our presentation to a close, I will summarize what we have achieved. We validated our theoretical principle through simulation, reinforcing key concepts such as duty cycle control, inductor selection, and ripple reduction. During the partial hardware implementation, we faced practical challenges that highlighted the importance of component selection, layout, and real-world testing. Overall, this project provided us with hands-on experience in power electronic design, taking us from equations to simulation to partial implementation. In summary, this assignment has comprehensively demonstrated the operation principle of a buck converter through analytic simulation and attempted hardware validation. Key outcome includes a functional step-down design that achieves targeted voltage and ripple performance, and a deeper understanding of duty cycle control, inductor capacitor interaction, and switching converter behavior, all of which are cornerstone of power electronics engineering. That's all for our presentation. Thanks for watching.